today, seminar from by the Professor Kudo from Ochanomizu University and Tokyo University, Japan. And the title of her talk is Observation of Localization Based on Quantum Dynamics. So, Kudo-san, please.
Thank you for the introduction. I'm Kazue Kudo from Ochanomizu University, Tokyo, Japan. And I also have a cross-appointment position in Tohoku University. And today's talk is about observation of localization based on quantum dynamics. And these are the references to today's talk. Here are the outline of talk. First, I will introduce the motivation and the aim of this work. And then I'll explain the models and methods. After that, I'll show our main results, time evolution based on exact diagonalization, and the time evolution using quantum circuits. And finally, I'll conclude my talk. Now, the introduction. Many-body localization is an extended concept of the Anderson localization, which is in a single particle system, so there's no interaction in this case. The Hamiltonian of this model consists of the hopping term and disorder term, and no interaction. If there's only hopping term, then a quantum particle in quantum lattice shows dispersive behavior. But when the disorder is strong enough, then the wave function localizes. That's the Anderson localization. In contrast, many-body localization occurs in a quantum system with interactions. So it is the localization in a many-body quantum system with large disorder. So here is the motivation of this work. First, numerical studies of the many-body localization often suffer from finite size effects. If we could use a large-scale quantum computer, then maybe a true MBL could be investigated. But the current quantum devices are too small and too noisy to compute exact quantum state, exact eigenstates. But actually, there are experimental works on MBL using quantum devices. For example, quantum annealer, trapped ion quantum computer, and superconducting qubits. And these figures show the experimental results shown in this reference. It shows the time evolution of probability density at each qubit. The initial state is 0, 1, 0, 1, 0, 1 with probability. And the dark color corresponds to the low probability, and the bright color corresponds to the high probability. And this figure corresponds to the thermal phase, because the initial pattern disappears soon. But this figure corresponds to the localized phase, because the initial pattern maintains quite a long time. Now, there is another example experiment using a quantum annealer. Actually, this work is inspired by this reference. They used the reverse annealing protocol with the mid-anneal poles. The initial state is all spin up or all spins down. And after post-quench protocol, measurement of the qubits produces the magnetization. So we can get the magnetization after the measurement. And this figure shows the average of the magnetization in the experiment. And horizontal axis corresponds to the disorder strength. So this figure shows the system is thermal for a weak disorder and localized for strong disorder. In the thermal phase, the average of the magnetization is almost zero. And in the localized phase, the magnetization is plus minus L. L is the system size. So it's the initial, it's the value of the initial state. So which means the memory effect. Now let's move on to models and methods. And the model Hamiltonian is given by this equation. Here is the interacting term and local field and transverse field. And here L is the system size. The local fields are given by uniform random numbers. And here W corresponds to the disorder strength. And in the following, we set J and gamma to be unity. And here we focus on two observables. One is the magnetization in the Z direction, which is given by this equation. And another one is twist overlap, which is defined by this equation. And here, U twist is the twist operator, and it's defined by this equation. Theta J is 2 pi J over L. L is the system size. And these are easily obtained through the measurement of each qubit in quantum devices. That's the point. And let me explain the twist overlap in more detail. The twist overlap is defined by these equations. And the twist overlap with psi being eigenstate. So if psi is eigenstate, then the twist overlap can detect the NBL transition. And Z is the twist overlap, which is almost zero in the thermal phase, because the twist operator causes a spin wave-like excitation. So U twist psi is almost orthogonal to the original eigenstate psi. But such a long wavelength perturbation, because it's a very long wavelength perturbation, which gives little effects on eigenstates in the localized phase. So in the localized phase, the twist overlap is not zero, but finite, but it has finite value. But the maximum value is 1, and it is actually the complex number. Now, and this slide shows the quantities evaluated using eigenstates. It's for comparison. The left figures show the entanglement entropy. It is the dependence of the disorder strength. And here we use the eigenstates in the middle of the energy spectrum. The upper panel is the average, and the lower panel is the standard deviation. Here in the thermal phase, the entanglement entropy is large, but it decreases soon when the disorder becomes strong, and then the entanglement entropy becomes almost zero. And the standard deviation has a peak around here. It corresponds to the crossover point between the thermal phase and localized phase. And these figures are twist overlap, average, and standard deviation. In the thermal phase, the twist overlap is almost zero, and it increases slowly as the disorder becomes strong. And the standard deviation also increases gradually. And this is not actually a peak, but it's just a saturation, because the maximum value of the mod z squared is 1. Now, let's move on to the time evolution based on the exact diagonalization. And the solution of the Schrödinger equation is written as shown here. Here, the psi naught is written as this equation, which is the initial state. And phi k is the kth eigenstate of the Hamiltonian. And ek is here, is the eigenenergy corresponding to the phi k. Phi k, yes. And in the following, the initial state is all up spin state, all spin up state. And the magnetization and twist overlap are evaluated using the wave function at the final time. And in this section, the final time is set to 10. Now, here this figure shows the disorder dependence of magnetization. And in small W region, which corresponds to the thermal phase, the average of the magnetization is almost 0, which means delocalization. And in the large disorder region, which corresponds to the localized phase, the magnetization is almost the system size, because when L equals 8, the magnetization is almost 8, right? This means the memory effect, so which corresponds to the localization. And the standard deviation has a peak around here. It corresponds to the peak of the entanglement entropy. And these panels show the disorder dependence of twist overlap. Here, in the thermal phase, small disorder region, the twist overlap is almost 0, and it increases gradually when the disorder becomes strong. And let's compare the panels evaluated using eigenstates. Here is the data evaluated using eigenstates. So they look very similar, but maybe the standard deviation is a bit larger for the data evaluated using time dependence, but they look really similar. So this means that the twist overlap evaluated using quantum dynamics provides some properties related to eigenstates. Now let's move on to the time evolution using quantum circuits. If we compute the time evolution using quantum circuits, the time evolution operator is approximated using product formulas. The first and the second order Suzuki-Torta decompositions are given by these equations. Here, m is the Torta number. And the single qubit rotation gates Rx and Rz implement the unitary operators, this one and this one respectively. And 2-qubit ZZ rotation gates implement operators for interaction terms. And in this section, we use a quite small system, L equals 5, and so the final time is set to very short, 1.5. Now, this slide shows the quantum circuit simulation results. These panels shows the magnetization, the average, and the standard deviation. Exact, the label exact means the exact time evolution, and these ones, the bracket Pn means the pth order decomposition with Trotta number n. So we see that these data in the magnetization is almost the same. So errors are negligible in the magnetization results. And these figures shows the disorder dependence of the twist overlap. This figure shows the errors are very small, but some errors appear. By the way, here ES means the data evaluated with eigenstates. But in any way, they look very similar. And the only difference is the standard deviation. The standard deviation for the eigenstates is a bit smaller than the others. But these are only simulations. However, the real device computation shows completely different results, because there are errors induced by noises. This figure corresponds to the magnetization, and especially here in the large W region, we can see the real device computation results is 3/4 of the exact results. But these shows some increasing behavior, but in the twist overlap, the real device results are very small, much smaller than the exact ones. So almost flat, not increasing very much. By the way, the difference between P equals 1 and 2 is negligible in both cases, and because these circles, solid circle and open circle, corresponds to 1 and 2, P equals 1 and 2, and total number is the same. But when the total number is the same, they are almost the same behavior. But this sky blue one corresponds to the m equals 15. So the total number is larger than the other two. In this case, these curves are a bit smaller than the small total numbers results. So the errors in the magnetization and twist overlap are more significant for larger total numbers. But why does the noise effect so different between magnetization and the twist overlap? The exact time evolution gives some hints. The upper panels show the magnetization, the time dependence of magnetization, and lower panels show the time dependence of twist overlap. These ones correspond to the weak disorder case, so it's in the thermal phase. In that case, they decay very rapidly to zero because it's in the thermal phase. And this corresponds to the localized phase, which is in the large disorder case. And in this case, in the panel B, the magnetization is almost equals to system size. It fluctuates around 5, right? Which means the memory effect. But in the panel D, some samples of the twist overlap oscillates with large amplitude, like this one or this one. So that's that causes the large difference. And the errors causes some effects on the amplitude of the fluctuation or the oscillation, both for the magnetization and twist overlap. But the errors in the amplitude does not cause a very big difference in the final values. But phase shifts of the oscillations or fluctuation due to errors significantly changes the twist overlap at the final time. That's the difference between the magnetization and the twist overlap. So it causes the large difference in the effects of the noises and noise-induced errors. Now, let me conclude my talk. First, the crossover between the thermal and localized regimes can be detected by evaluating an observable after some time evolution. In this talk, we focused on the magnetization and twist overlap, and they can be easily obtained from the measurement of qubits in a quantum device. And the twist overlap evaluated using the wave function of the time evolution behaves similarly to that calculated using eigenstate under some condition. So the twist overlap may give some information about the eigenstates. And the latter half of this talk shows that choosing an appropriate observable is essential for detecting localization using a real device. And the magnetization is robust against noise-induced errors. However, the twist overlap severely suffers from errors. So that's all. Thanks for listening.
So thank you very much. Very interesting talks. So I'll take questions from audiences. So any question, comment? Okay, Paul, please.
Thank you, Professor Kudo. Very interesting presentation. I'm learning lots, I think. So is it possible at the end of running on an annealer like the D-wave annealer, is it possible to calculate the twist overlap on the basis of these classical states at the end of the annealer, or is that not possible?
I think it's possible because the reference I introduced is based on the magnetization, but this is actually these experiments performed by D-wave vanilla. In this case, they observed the magnetization, but they used the measurement of sigma z, just the qubit, and here. So twist overlap is defined by this, but it shows it consists of only the sigma z. So we can see we can obtain the measurement of the z component, then gather and calculate this value. Then we can compute the twist overlap, actually.
Good, good. So the result from the other group that you showed a second ago, the magnetization,
yeah,
I believe that is completely an artifact of reverse annealing, nothing to do with localization, because there is a memory effect of reverse annealing as well that's pretty well understood. So it would be interesting to see if the other metric, the twist overlap, also shows some kind of memory effect. I think that's an interesting question, I think.
Yeah. Yeah, I really want to try, but it's expensive to do many experiments.
Yes. Thank you.
So, okay, so good. So any question or comment from audiences? So I have a simple technical question. So you perform the new experiment using the actual quantum devices. So which quantum computer did you use for this calculation? So IBM?
Yes, IBM quantum device. Yeah,
okay.
Yeah, only 5 qubit
Okay,
device
just
was for free at that time.
Yes, I see. And you mean that the Brisbane or Kyoto or Osaka processor, like something like, yes, you use
Yeah, something like that.
actually. Okay.
In this case, the device was just a chain-like 5 qubit system.
Yes, right. And then my question is that actually that okay, you can use the I think the 4 or 5 quantum processor for the IBM Qiskit, and then you can choose one of them for the, and then each processor has different fidelity, right? And some processor is maybe the Brisbane is a very good quality, but the other one like Kyoto and Osaka is very low quality, very low fidelity. So there you can perform the both processor and then check the difference, and maybe that you can get some information from the effect of the decoherence or noise for the detecting the mid-body localization. So did you try it?
Not actually. At
Okay,
that time, yeah, at that time I tried some other devices, but it was low quality. In this case, this experiment was performed on the 5 qubit chain-like structure,
yes, right.
but other ones are like some different structures. Then there are some crosstalks.
Maybe a hexagon or something like that. I see. Okay. But very interesting. Maybe that you can also perform the using the like the QERA called atom quantum. Yeah, so very interesting because they so actually in this sense that in order to detect the signature of many-body localization, the NISC is not enough, but the FTQC is necessary. So that is your final message, right?
Yeah. Yes.
Okay. Yes. In this sense, that QERA cold atom quantum computer is one of the best choice. So
Yes.
I hope Yes, good. So any questions or comment? It's okay. So if not, so okay, yes. So time is just now up. So then, so let's thanks to the Dr. Kudo again. So thank you very much.
Thank
So
you.
very, very interesting talk. So by the way, Paul, do you have any announcement from INQA?
Yes, maybe a quick announcement. So
Quick. Yes, okay, please.
next week we have a seminar given by Phys CTRL. I can't remember the name. It's giving a presentation, but that should be interesting, looking at their benchmarking of QA.
Benchmarking, yes, the IBM and the D-Web, right?
Yes. And
Yes.
then have a break. So there'll be no seminars in August.
August, yes.
The next week's seminar, and then we'll start again in September with the usual weekly seminar series. There will be a change in the timings of the new seminar series from September. In case, well, there'll be an email describing this, but essentially it'll either be at 9 AM in the UK, or it will be at 5 PM in the UK. I'm afraid I don't have the correct timing conversions in my head. But rather than having 3 different time zones, we're just going to stick to 2 moving forward from September. Good, thank you very much, Shiro.
Thank you very much. Yes, thank you very much. Okay, see you next. Bye.
Thank you.
どうぞありがとうございました。どうも。